we start with questions. Something that is bugging you. Let me see how many are here. I have to ask you something. Okay, I'll remind you later during the break what we need for the office hours. Do the following, write on the chat the preferable day of the week, maybe 2 days. 1, the best, and 2, the second best. Because I'm not sure that Thursday is best for you and you were not sure about Wednesdays. So think a little bit, please. We'll make a poll. I'm reasonably flexible. And office hours are important. By the way, you can also try me on other occasions. Okay, you can write to me and we can try to meet if you have questions. Office hours just means that I have to be there during those hours. But I, you know, I'm usually around. So I remind you during the break again, if more people show up, because I'm about to start. Because it seems that also Monday is reasonably light for you guys. I can also do it on Mondays in principle. I guess, okay. You just guys do what you like and then let's check the sharing. Let's make sure everything is okay. It seems to work, am I right?
Yes, sir.
Good. Let's go to my good notes. Lectures. Lecture 5 today. Well, I got an email address, joint email address, so I can send you my notes. And I can send you other notes. I will be sending occasionally things, ideas, what to read and so on, original literature, okay? But I needed the colleagues in the computer section prepared the joint email for those of you in diploma and those outside. So let's go. Since there are no questions, we are going to start. I promised to think a little bit. I don't want to do very much because I think this could be a good homework. I'm thinking about the second homework and the subject of today. So let me just write down. This is lecture 5. And a few words. I will give you the homework, I think. I will decide and then talk more after the homework, okay? But today just outline the discovery of W and the proof of parity violation. And of course, that means that you understand how to produce it. We talked about it yesterday. And even more important is decay, right? W is an unstable particle. By the way, why do I speak of W as a particle if it's decay? Unstable particles. Normally, in the old days, you will call a particle something that is stable, so it keeps existing. Unstable particles, by definition, is still a well-defined particle that you can study as long as the decay rate is much smaller. So gamma W should be much smaller than MW. Like W here, okay, in principle, gamma of that particle should be much smaller. So you have a small decay rate, so it's a well-defined, you know, that particle, of course, is what we call Bright-Wigner resonance. Okay, it looks like this. Okay, it's not just one line, it has a decay width. The cross-section for the production as a function of energy peaks around MW. But there is a width, gamma W. As long as that is small, you have a well-defined kind of Gaussian distribution. I have a question for you guys. Can you tell me what would you expect without calculating? So you're lazy persons. It's called lazy men's, lazy women's, lazy persons approach. It's very good from time to time that we do the lazy persons approach. Tell me, what would you expect for gamma W without knowing anything? W decays into particles like what? As the electron and antineutrino, remember? Or down quark plus anti-up quark, W minus, let's say. So here, what would I expect without doing a calculation? You can say anything comes to your mind if you feel like saying. I want this part of the lecture because I don't want to reveal everything because I want you to do the homework. I want it to be sort of light. One of those lectures which I improvise, I told you, which are not very systematic or rigorous, that we need to do that in order to make the course more interesting and also to sort of think a little bit. And typically I'll do it before the homework. Then after the homework, we organize what we learn. What is the unit? Obviously, the unit is the same, right? By the fact that I wrote here from this, obviously the unit of the decay width is the same as the mass in our natural units, right? The decaying particle has a wave function that goes as e to the minus gamma t. So the unit of decay width is inverse of time, which is an inverse of space, dimension, which is mass, right? The dimension of mass is dimension of length to the minus one. I should have said this, but you know this, right, in our units. It is simply, it is simply that h bar is 1, which means that PQ is a number. So that the dimension of P is the dimension of distance to the minus 1. But P is MV, and I work in the unit C equal 1. This is just a reminder, right? So dimension of P is dimension of M, and so on. Our fields have dimensions. We'll talk about that, okay? This you know, but just reminders of the basics. So the dimension of the decay width is the same with the dimension of mass. Therefore, I expect it to be
2M.
MW, right? Because the fermions are much lighter. Remember what I told you yesterday? Even the down quark and up quarks are very light. But even a charm quark is very light. We'll talk about it. And of course, the leptons are light. Leptons comes from the word leptos in Greek, which is kind of very, very thin and light. So this must be proportional to MW. Very good, because of course, it's not really MW, it's maybe MW minus M electron or something. but I'm ignoring, this is in the limit, which is the limit you and I like to think about, that electron is massless and the quark is massless. The first approximation that you and I want to do at the tree level. But what should be the constant of proportionality?
G squared. Or...
Precisely, alpha, something like alpha should emerge. Very good. Because there is nothing else in the case of the coupling constants. Very good. And you see why? Because we are in the weak, in the perturbative coupling regime. We are fortunate that the weak coupling G, electromagnetic couplings are small, and therefore this justifies this. I know this will be true without doing a calculation. This is what the lazy person does. Doesn't want to sit down and do the calculation. Okay, we'll do a few now lazy person's approaches, thoughts, okay? So W is a well-defined particle. I mean, I expect alpha is of order. I expect roughly that the width of W is of order GV or something, okay? Alpha is of order, maybe few GV, okay? Let's say, I don't know, few, obviously much smaller than MW, which is on order 100 GV, we said MW roughly. This is well satisfied, okay, very good. That's essential, okay? So it makes sense to keep talking about the production and the decay of this particle. You know, when the decay width is as big as the mass, we call these resonances. They don't even live enough for you to study them, detailed properties, okay? Like if you decay through strong interactions, then of course, all hell breaks loose. I forgot to write, the dimension of V is 0. It carries no dimension, velocity. Okay. So we said yesterday, I have a down quark, comes from my proton. I prepared this accelerator, synchrotron I called in the beginning, okay? More than worldly is the accelerator. I hit a proton on the antiproton. I can even use the proton, you know, I don't have to use antiproton. We will talk about that. Even inside proton, there are antiquarks. These are quantum objects. You never have just, say, an electron. You have a cloud of particles and antiparticles around them, okay? But if I have an antiproton like the original discovery, then I'll take U bar from antiproton and I'll hit them headwise. So remember, this is left-handed. This is what Marshak and Sudarshan taught me. This, remember, is right-handed because it's an antiparticle. Psi L, C, the antiparticle, C, psi L bar transpose, we found out, becomes, look how the bracket changes the place, becomes right-handed. This is very important. This relations is crux of it all. You wanna keep that in mind. Therefore, this is very good. You people helped me yesterday. Because of the helicity being -0.5, the spin goes in this direction. Because of helicity being a +0.5 for the right-handed particle, the spin goes in this direction. So if I'm along the z-axis, I actually have W. When I produce W here, I produce some heavy object called W. I have enough energy. It will be polarized. The spin of the W is +1. Actually, along that axis, since LZ is 0, I will produce W at rest. But even if it moves, you and I know how to boost things, okay? We'll assume that W is at rest, and someone asks us, well, what if W is moving? Okay, we do the boosting. This is trivial. That we learned when we were, you know, kids. So from here also, I know that the total angular momentum of W is conserved. because they didn't carry any angular momentum quarks along the motion, line of motion, which I call the z-axis. And now, okay, this helps me a lot. You see what I mean? In this particular case, the way I took it, I know what is epsilon mu of W, the polarization tensor. Remember at rest yesterday? This is the guy that has spin 1. It's very easy, and he had some normalization factor, as usual, which is what I need if I want to start computing the decay rate. And now W decays. The next step is W decay. So let me try to think about the electron, the simplest of it all. This is surely massless. M nu is practically 0. We said that M nu less than 1 electron volt. This is 0. M electron is MeV, but that's 10 to the minus 3 GeV. And you know, since MW is 80 GeV, that means that E electron is E antineutrino roughly of 40 GeV. The mass is very small. Let's write this more neatly. E electron is roughly in your bar is 40 GeV, which is an excellent approximation to take M equals 0. After all, it's some 5 orders of magnitude. In other words, what I mean is that ME over EE is roughly 10 to the minus 5, and 10 to the 5 for me is 0. I'm not even going to compute the loop, which is maybe 1%. Okay. Well, I can write like this to make you happier. And that simplifies our calculation a lot. Now let's think about it. I have a W polarized like this. I have a sense of direction. Let me call this Z axis, now pointing up. It was pointing to the left, but as a matter, we can say it's up. So let me ask you a question. Let's analyze you and I. Let's try to see. Let's imagine what can happen if I look along this axis. I can have electron going up, antineutrino going down. Or electron goes down and antineutrino goes up because the conservation of momentum, energy of W is equal energy of electron plus energy of antineutrino, and the momentum of W is the momentum of electron plus the momentum of antineutrino. They are going opposite from each other. They are massless. Okay. Tell me one thing. Now this is left-handed, I know. I've known it from 1957. This guy is right-handed. I know it from I wrote about. When I do this charge conjugation, you and I checked it already a few times. If there is any little down, please check it immediately during the break after the lecture. I know that this guy has to be left-handed and this guy has to be right-handed. So let's look at the first piece. And notice I'm looking at the z-axis. So the angular momentum, Lz of electron, is Lz of antineutrino is 0. So where is the spin of the electron pointing in the first picture? Tell me. I need help. No, this is going up. I'm sorry. I'm very sorry. Who's gonna help? Where is the spin of the electron pointing?
It's pointing down.
Pointing down. What about antineutrino?
Pointing down too.
So tell me, can this take place?
No.
Right. HZW is SZW is +1. And we just found out that HZ of electron plus HZ of antineutrino, which is SZ electron plus SZ of antineutrino, is -1, we just found out. -0.5 from -0.5. This cannot take place. Here, from what you told me, this should be pointing up. Obviously, all I have to reverse. Can this take place? Yes. So if I look along the z-axis, all the electrons want to go down. This is what is very hard to compute in the nuclear decay. It will drive you crazy, okay? Here you will compute this, okay? You are gonna see the discovery of parity violation. If parity violation is maximal, as I kept claiming, the guys at the original, at the lab, for example, or LHC today, they should not see this. And that's what happens. Nobody has ever seen. We'll put some limits, we'll talk about that, okay? That doesn't mean that it's zero. You keep looking for, maybe it's some small numbers. But, you know, let's say this is happening. This is happening now in less than 1 in 1,000. Probably even smaller, but around 1 in 1,000. We'll update this number, okay? LEP sees, actually the original discovery was the machine called SPS, proton synchrotron. What was the S? I even forgot. This was in 83. This was a PP bar machine. Had an energy on the order of 100 GeV, 7 kilometers circumference. There were 2 teams. There was Rubia, Darula. The team had names not very imaginative. They called team 1 and 2. For some reason, they picked one name. One of these interesting ways that people give Nobel Prizes. Rubia got a Nobel Prize. Darula didn't get a Nobel Prize. There were also other people, important people, De La Negra, the spokesman for the experiment. But anyway, Darula, a great French physicist, was on the other experiment. They have established this. They already saw this interesting thing, the maximal parity violation, which means that along z-axis, remember what the z-axis is? That's where the spin of W is pointing, is along the z-axis, electrons go down. Is that what we concluded? Let me check. Yes, they go down. Up to now, all of them. We've never seen an electron going up. This is the fundamental result. Confirmation of the Madame Wu and Lederman, especially Madame Wu, the great discovery of parity violation in 1956. Okay, it's beautifully confirmed. Let me ask you, let me ask you here. I wonder if you would want to make a guess. You know, I have looked at this. So I have my z-axis. z-axis. So I can look at the electrons going, say, like this with the angle theta. Let's imagine this is the electron going up, and then this is antineutrino going down with an angle theta. Can you guess, if you look at the partial decay rate, d gamma over d omega, would be proportional? Can you guess the dependence on theta? You know, they cannot go up on the z-axis, but they can surely go in this direction, because here, of course, they carry angular momentum. So I cannot say that they cannot go in this direction. This is possible. What is not possible is going in the up direction. Can you guess? You want to try? Lazy person's approach. We have a lazy person again. You know, it's good to be a lazy person before doing the calculation. You know why? Because we may make mistakes in the calculation, and it's good to know what is being expected, because that won't fix the coefficient. But you have a great check of what you are computing, so that you don't hand in, you know, senseless results. Wrong is okay. Senseless is a pity. Your professor is less happy, or your tutor.
Momentum of electron and also spin of W.
No, I don't. There will be other things. No, I'm not asking you that. We'll think about it. By the way, there is no momentum of the electron. There is only MW. Everything is MW. You don't have to think in this term. Remember, this is equal to this is massless, P of the electron plus P of the antineutrino, which are equal. But from here, I know that P of the electron, the absolute volume, is equal to P of the antineutrino. So in other words, I know that the energy of the electron is the momentum of the electron, it's MW over 2. So from now on, let's remember, this is what he did for the decay rate, that the only dimensionful parameter is MW. Everything at the end will be determined. No, I meant the dependence on theta. What function of theta? This is proportional to, oh, I'm sorry. I should have asked you like this. I confused you. What do you expect f of theta?
Is it sine of theta?
Aha. Let's think about that. Oh, okay. Okay. The first guess, proportionality, so it can be sine theta. By the way, you know, maybe it should be, if it's sine theta, let's see what will happen. If it is sine theta, then it cannot go up. It's correct, you agree. This would work, but can it go down if it is sine theta? No, sine of pi is 0. So this must be wrong, since this implies that E cannot go neither up nor down. But that's not what happened. They all want to go down. So this cannot be. Someone wants to try? It's not a function of sine theta, that wouldn't work. Well, sorry, everything can be written as a function of sine theta, but it becomes ugly. I wanted to say something silly. Think of cosine theta is better. I'll give you a hint to help you. One minus cosine theta. Remember, it has to be maximal when theta is pi. So it has to be like this. And it's going to be a square. It's a positive quantity. You will get a square. that really becomes the maximum and not some negative number, it's not surprising that it comes out at a square. This ensures that, in other words, f of theta equal 0 is 0, and f of theta equal pi is some number like 4, which is maximal here. I can write, because there is proportionality there. Okay, this is what we should get out of the calculation. This is what I want you to compute for the homework. I will outline the calculation now. You will start with the interaction, which is g over square root of 2. Then you have, say, u bar electron. Let's call it momentum p, gamma mu, v anti-state of neutrino, momentum q. By the way, I mean, p is equal to q, or p plus q is 0, just to remember. And there is epsilon mu of +1. And then we are going to, we will sum over all the polarization, all the spin, we sum over the all final states to make it simpler. We are not interested in polarized. So in other words, the amplitude square is a sum over spin, g square over 2 will come out. We'll have u bar of p. I gave the name p and q, just, okay. Then there is epsilon slash, you agree, gamma mu epsilon mu. Then there is v of q, v bar of q, epsilon star slash, the anti, u of p, sum over spin. Remember what is sum over spin? V of q, v bar of q. Who can remind me of this? It's a matrix. It's very easy.
Q
It's
slash,
sorry?
Q slash plus M.
Q slash, massless. Massless, very good. I'm glad that you remember that there is a mass term, but it's massless. This is neutrino, surely massless. I'm working once again in the approximation that the mass is a 0. For neutrino, there is no doubt. But even for the electron, it's too small a correction. Very good. And similarly, sum over S, u of p, u bar of p is p slash. I forgot, sorry, there was left-handed. I forgot to put this L here. And there was L. What I mean is that, like UL bar, gamma mu, what I wrote, if I write, no, why don't I write? What I mean is the following. When I have psi 1 L bar, gamma mu psi 2 L, this is psi 1 bar. It becomes right-handed because of gamma 0. There is gamma mu, there is L psi 2, which is psi 1 bar. R goes through gamma mu, L times L psi 2, which is psi 1 bar, gamma mu. L square is L psi 2. Because we like to use these trace formulas for components, I have to make sure that I keep the, so what we get, that my amplitude is g square over 2, and then I will have the following trace. I have to take the trace. I'm 5. You've done these calculations, of course. There will be p slash, there will be epsilon slash, there will be L, there will be q slash, there will be epsilon star slash, and there will be L, something like this. and I gave you epsilon. So let's take what you need. Once again, epsilon mu is epsilon mu, what I call +1. Let's write it here. It was 1 over square root of 2, 0. To simplify things, what should I write here? There was 1, there was I, and 0. Okay, what about P? P mu. The value of the momentum is half mw. There is a function of theta here that I should write. The z component is what? Who's going to help me? It's cosine theta, right? I have a vector pointing. My electron was pointing in this direction, so the z projection is cosine theta, as you know. And the x must be proportional to sine theta. There is also cosine phi. Maybe I should write the whole thing. I'm sorry, I wanted to sort of be smart, but let me not be smart. That may come in a second. The value is mw over 2. So this is, why did I, this is 1. That's the energy. And then it has sine theta, cosine phi. Sine theta, I'm going to take spherical coordinates, sine phi, obviously, cosine theta. And q mu is mw over 2, 1. What about the, well, just the minus sign. Everything is a minus sign. It goes in the opposite direction. Opposite. Please remember P plus Q is 0. So here is opposite sign. Tell me one thing, will the result depend on phi? The final result, when I compute the partial decay rate?
It should not.
It should not, because there is still a rotation around the z-axis symmetry. I had a rotational symmetry in the beginning, of course. I have a Lorentz invariant symmetry, okay? I'm at rest. So I broke the Lorentz symmetry, the boost symmetry, I'm sorry, I'm at rest. There is still rotations. But what I did, I polarized the W along the z-axis. So that fixed the z-axis. You know, where did I say it? I said it here. This was my polarization of W. So I broke the rotational invariance, but I keep the rotation around the z-axis. So it cannot depend on phi, no. So when you do this calculation, you can fix your phi if you wish. You can take phi equals 0, whatever. You guys decide. Because you know, you can argue this is not going to depend on phi. I'm lazy, you know. So the lazy person says, you have to sort of, well, I help you to explain it, okay? Because you can't just do that. Your lazy person says, I'm going to take, you know, phi equal whatever phi lazy like to work it with the simplest. You can fix it to make it easier, but you see, you have everything here. All you have to know how to take traces, but you know the traces of 4 gamma matrices, right? You agree that you know this, please?
Yes.
Please tell me yes, because there was what, some 4, I remember, gamma mu nu, gamma alpha beta, and then there is this cyclic thing, okay? I don't have to write it. There will be also trace to take of gamma mu, gamma nu, gamma alpha, gamma beta, gamma phi, because I have a projector. Notice there is just one projector. L goes through. L goes twice through. So I will just have L. What is this? Can someone guess what this is if you've never seen it?
Probably there is this antisymmetric Levy-Smith.
Yes, yes. I don't remember the coefficient, you know, we'll remember the coefficient. Okay, I can send you some notes. I'll try to send you some notes that I give you the input with our conventions, okay? So there is some very good, it must be epsilon mu nu alpha beta, right? This is parity odd, obviously, okay. It's very easy to see. Take, you know that, take two of them equal, and you will have the trace of 3 gamma matrices, and that will be 0. Take 4 of them equal, trace of gamma phi 0. This is just the traces, okay. So it's well defined. So from here, m squared is just a function of theta. It's not a function of phi. Dimensional quantity is mw, okay. There will be a dimension. I don't want to help you with a dimension, but you know it's going to be a function of theta. I even helped you that it's proportional to f of theta, and I even helped you that, you know, we'll get to 1 minus cosine theta. I wanted you sort of to make the life easier for you. And obviously there's gonna be a kind of play between these two terms. One will go as cosine squared, the other is cosine. Maybe you can guess which one. You start guessing, don't say it loud because this is a homework, which will give which. This will be the homework. And then of course, once you have that, you can compute d gamma over d omega, which has I'll give you the formula. It's a well-defined formula. Here are some integrations. There will be some integrations, obviously. I don't know. You probably know it. You must have done two-body decays. Have you? Have you done any two-body decays at ICTP? Yes or no?
We saw the formula for two-body decay.
But you didn't do it. I will give you the formula. I don't, you know, I remind you. Anyway, you can look it up in any book in the world, but I'll probably give you the formula. Let me see how I'll organize this. I'll tell you where to look. I don't care of you people knowing things by heart. Okay, it's a well-defined, easy thing. Okay, and the calculation is very easy because there is a conservation of momentum. Remember that P of W minus P of electron or minus P. No, why do I write like this? Minus P plus Q. Well, there is a delta 4. Why don't I like the momentum? I don't have to. I don't want to do it now in some not organized manner. I want to send you some clean notes. Okay. This obviously will be proportional to 1 minus cosine theta squared. This is what you compute, and then you ask Darula and Rubia to check it, and they will tell you, yes, this is what they got. This is what SPS and then LEP, LHC has been confirming ever since with fantastic precision that you compute for them. So see, you're doing the calculation, which is sort of nice. That was yesterday a great discovery. That's made us believe in the standard model. That was the crucial point when you were sure. Most of us believed even before over the indirect agreement, but the discovery was spectacular. This is what you get. So this is experiment confirms once again maximum p violation. Then, of course, this is just, we just computed gamma W going into E. Then I can into nu bar is the integral over d omega. That's very easy. D gamma over d omega that you compute it, and that will give us a number. I don't remember, I think it's alpha over 12 or something. I can't remember, gamma W. Of course, please, this is to be checked. Then you will tell me, oh, but let's not forget, if it's really the W and I want to compare with these guys at the LHC, don't forget that there is also down quark plus anti-up quark. Imagine that they are equal, that they are massless. What should I expect for the result? Is it equal to W into E plus nu bar? They are massless. Am I right?
Yes.
Because what is the difference between electron and the down quark if they are massless? True? Agree? Wrong. I cheated, you know, I use the, let me put the question mark, why? After all, they really look the same. Well, the quarks carry color, that you know, even without studying deeply the QCD theory. He must have told you, you know, I think at least 20 times during the course, Smirnov said that quarks carry color. I can bet. I can ask him. You know that, right?
Yes.
Yes. How many colors?
3 colors.
3 colors. 3 corresponding to the SU3 symmetry. Color is just a fancy language. Red, yellow, blue. They just come in 3 species. When I speak of weak interactions, I can ignore it. Just the way I ignore the Lorentz index. So W going to this guy, therefore, W going into down quark plus U bar is 3. Because it has an option to decay into, this is very important. Now I want to talk the real W. So W, there is also second generation. I will forget my pretense. That consists of the charm quark, strange quark, muon, and another neutrino, call it nu mu. So this will be nu E bar. Here, just mass of the muon. What is roughly mass of the muon? Well, it's pretty good. I can write. Who knows?
105 MeV.
Very good. You have any idea what is the mass of the strange quark? I didn't even speak of the masses of quarks, but just if you heard or someone mentioned, I don't know, you know, or you read somewhere. Any idea?
101.
Yeah, very good. No, don't be so precise. No, that cannot be. You will see also it varies at which energy you are looking at. Mass is a funny thing. Okay, so let's say 100 MeV.
100.
When you come to quark, you cannot be precise. I'll try to explain that. By the way, mass of the charm quark, do you have roughly an idea? Again, I just interested in the kind of order of magnitude. Don't have to be a precise number. It's heavier than the strange quark.
1000 MeV.
Yeah, very good. Nu mu, neutrino is basically 0. I don't want to talk about neutrino. Neutrino is massless for you and me. Neutrino is always massless unless we speak of oscillations. It's so small that you need to do this crazy thing of neutrino oscillations. There's some funny quantum mechanical object that I'll remind you again. You've heard it. So this is 1 GeV roughly. So you can take that the mass of the second generation is 0. It's much smaller than MW. You want to include them. I want you to do I want you to compute the W decay rate, and then you go and do the particle data and you say, oh, yes, I got it. And then the third generation, This is as good moment as any to give these numbers. There is top, there is bottom, there is tau, and there is nu tau. Any idea about the mass of the top? Well, mass of the tau, let me start with the lepton, roughly. Anybody wants to try?
100 GeV.
100 what? Sorry, 100?
GeV?
No.
No.
All the fermions of the standard model are light, except for one. M tau is GeV, maybe 2, 1,8. I think the number is 1,8. Remember, I don't care for you to know the numbers. I like you to know the sort of rough values. MB, again, I can tell you if you don't know. All the fermions are light. There is a very interesting thing compared to MW.
4?
Yeah, something like 4 or 5 GeV. M nu tau is 0, right? I don't know why should I write it even? Okay, all the neutrinos are massless for us. And M top, let's write separately. M top is roughly
100 GeV.
Yeah, it's even bigger. I will emphasize the number because you're right, 100 GeV is a good thing. It's almost 200. It's like 175. Just to sort of tell you why I want it to be, just to make sure that you know it's heavier than the W. Therefore, can W decay into the top plus bottom? No. Top is heavier. So when you compute the decay of W, of course, it will go into all these guys. It will go into tau and nu tau. So in other words, W will go into tau plus nu tau bar, but W won't go into top plus tau bar plus B. This you won't include. This is very important, otherwise you'll make a mistake. And when the dust settles, at the end of the day, gamma W total is some number which I forget, alpha over pi, something like this, I think comes out. Please forgive me here, not knowing the precise number. I don't care about precise numbers. We can always sit down and compute them, but we get a, maybe there is no even alpha over pi. Look, there are 2 question marks. Okay, I would say that the pi should come out. I could be wrong. Even pi. Let's put this thing here. You know, is there a pi? I want you to help me. You can, of course, find it somewhere in the books, but it's more fun if you guys compute it. We'll give you the formulas to play with. This is the W decay. What do I want to say here? I don't think I want to say anything else. When you look at the second generation, again, remember that there are 3 colors for charm and stretch. All the quarks are colorful. You just forgot, you know that. By the way, you know, when I ask you, I may ask you, by the way, why don't I do that? Why don't we chat for a few more minutes? We make a break, but this is a good moment to go on a little while. It's not a heavy lecture. I don't know if you need a break today. The lecture is lighter. I'm just sort of sketching things. I don't know if you get bored when it's sketched or you're bored when the calculation. We need both to do physics well. To do physics well, you have to oscillate between being lazy and extremely hard work. If you work hard all the time, you will never arrive anywhere. If you're lazy, of course, forget it, that you know. You need a mixture of the two. So how do you know that quarks carry color? Tell me. Apparently. Why did I say that? How do I know? Any?
Is it because of strong force?
Yeah, right. But how do you know that they carry color? It's not that because of the strong force. You know that the strong force, the theory, you know, how to say it. Remember it is facts, my dear Watson, says Sherlock Holmes always. I can't overemphasize that. If there were 4 colors, the strong force would not be SU3, it would be SU4. First you know the fact. Remember that. You build a theory along the facts of nature that may lead to other predictions, but not a starting point. You know, if like me asking you, let me ask you, suppose I tell you, how do you know that electron is a spinner? And then you say, because of the Dirac equation. No. Electron carries spin. They actually, Goldsmith and Uhlenbeck came up with a spin, and it was proved to be there. Some observational experimental evidence. Why did they suggest originally quarks carry color? It's crazy. You don't want to come up with color, which complicates your life. Something was there that made them say that.
Because of Pauli exclusion principle.
Yes. Where? What?
We can have, for example, I don't remember the name of the particle, but particle that has 3 U's.
Oh, good. Oh, good. It's called delta. I don't care even. It's doubly charged, right? Because there are 3 up quarks. Very good. And you wanted to have an anti-symmetric wave function. This was a state of it was a symmetric S equals 0 state, symmetric. But Pauli, this fermion must have an anti-symmetric wave function. And the way to make anti-symmetric is to anti-symmetrize here. Alpha beta. So what you do here, let me erase this and write it below. There is this epsilon alpha beta gamma anti-symmetric tensor. This is the way to make it anti-symmetric. This is anti-symmetric tensor. Alpha 1, 2, 3 is a color index. This is why they introduced the color. And then once they introduce this, the proofs came. For example, when pion decays, for example, pi 0 decays into 2 gamma. For example, how does pion decay to gamma? It's a neutral particle. It couples to. It's made out of quark and anti-quark. Pi 0, after all, it's U bar, D bar combination, which can produce 2 gamma. Notice that you will sum over color when you compute this rate. And this agreed with 3 colors. Oops, why did it not happen? Interesting. Oh, I went into, what happened? I went into something else, lecture 5. Oops, I must have touched something. All right, sum over color, disagreed with 3 colors. Computation versus observation. By the way, you are going to now prove W decay is a beautiful conformation of 3 colors because it decays into the electron plus antineutrino and then down plus U bar. And of course, other generations, okay, that we just talked about. You will get the agreement here. You will have, okay, anything, you know, you can imagine a lot of decays that people can think about. By the now, there has been plethora of processes. It started here, anti-symmetric wave function over fermion. I'm sure Smirnov talks about it. All of that agrees with three colors. So it's nice to see yourselves that it agrees with three colors. This is why I like you to compute the WDK. Also to check the color. I'll come to talk about the theory of Strock interactions later. I don't need it now. Because the SU3 symmetry, which is the source of the SU3 gauge symmetry of the strong force, the 8 gluons, is orthogonal to the weak interaction. So when I'm computing decays, okay, color plays no role. I just have to remember to sum it. It's just a number of states. I suppress the index just to first I suppress the spinor index. So how do I recover the spinor index? I recover the spinor index because I run into the trace formula like this. I don't have to introduce the spinor index. I just do it at the last moment when I need. It's here. You see, if it was a scalar, it would be a number. There would not be some polarization. Here is a matrix. The same way with the color. You just give me a number. Okay. This is probably all we want to say about the W. I can say a few words about I can go on a little bit if you guys are okay. It's okay that we go on because it's light, or you want a break? How do you feel?
I think it's okay.
Others?
Go on.
It's okay.
We can go on. All right, let's go on. If you tell me that you get tired, please, you are allowed to insist on the break. I'm allowed to suggest it. You're allowed to suggest it, okay? I feel that today, it's even a pity to interrupt the flow in our little discussion. You see, by asking you questions, you know, you are sort of getting there on your own. So the Z boson, it's a little more complicated, okay? Z boson, of course, decays into fermion plus anti-fermion. It's always the same species. Remember, the interaction is diagonal. This is like the photon. And we had the interaction. Let's remind ourselves, there was a coefficient G over cosine theta W. If you remember, it's a little stronger than the weak interaction. The neutral one, it's not G. And then we had F bar, any fermion neutral, as long as I know it's T3. And remember, I can put L, but I don't have to because T3 picks up left-handed. So I'll put it now just to emphasize the chirality. Then there is a piece which depends on the charge. Charge, of course, is left-right symmetric, so there can be no projector. You see, you know that from QED. Left and right fermion have the same charge, but left and right fermions have different 3. T3 of left-handed fermion is either plus a half or a minus a half. They are doublets. T3 of right-handed fermion is 0. They don't know that there is SU2. That's why I call it SU2L. And of course, QL is equal QR. That you know from QED, that you knew always. Okay. So here now the interaction is more complicated. It's not just L. So, you know, I can write like this. I can write G over the cosine theta W, this interaction. F bar, gamma mu. I can write A plus B gamma 5. F. For W, A and B are equal, well, B is minus A. Here, of course, it's not true. So, you know, how do I reproduce that? Well, this is equal to Z mu. And in other words, this is equal, this piece is equal to No, let me write better. You don't need all of this. This is equal to A plus B comma 5 is equal to T3, 1 plus gamma 5 over 2, minus Q sine squared theta W, which is what it is. So this is equal to T3 over 2 minus Q sine squared theta W plus T3 over 2 gamma 5. So notice this is A. This will be A. And this will be B. The way I wrote it. You know them. So we have to, in the Z boson decay, the formula is a little more complicated because there is A and B, but they follow the same thing. I don't have to write it. It's just a little longer calculation. You know the coefficients, just call them A and B, and you would compute d gamma Z over d omega as the function of A and B and theta. The dependence will not be the same because it was very easy when you had a maximal breaking of parity. In the case of Z boson, this is not true. It's not simply 1 minus cosine theta square. It's more complicated. I don't know how much input I will give you. We will talk about that. You can see that it's straightforward. Everything is the same as in the case of W. It's just the interaction is a little more complicated. Again, the mass of the fermion, you'll take it to be 0. In other words, I'm saying that the even mass of the bottom quark, because it's much smaller than MWMZ, I'm saying there will be a correction. You're going to make a little mistake. People incorporate that mistake, but I don't care. And remember that Z, can it decay into top plus anti-top?
No.
No, that is. Also, you must remember when, so what does Z decays to? Z decays into electron plus anti-electron, neutrino plus anti-neutrino. It's always particle anti-particle. Down quark plus anti-down quark. Up quark plus anti-up quark. That's the first generation. Then muon plus anti-muon. Nu mu plus nu mu bar. Strange plus anti-strange. It's the same thing. It's just you're ignoring the message. So there is no new. Why am I writing this even? Charm plus anti-charm. Well, just to remind you, there is third generation. Okay, all the same. But no, here is all the same repeated, but no T plus T bar. This you don't have to include, and you have to remember that quarks has 3 colors, and you can compute the decay width of the Z boson. So you will compute from here d gamma Z over d omega, and from here you will compute gamma Z. Now notice a beautiful thing that you can do. And this is sort of nice to check yourselves. In the old days, today we know that there are 3 generations, not 4, not 5, etc. How do we know? LHC. It's going to very high energies. It is proving. I'll teach you this in the standard model. This is yet to come. Don't ask me now to explain the details, but we know that there are 3 generations. Of course, at LEP, you didn't know that. There could have been more generations. So there was an interesting question. If I have 4 generations, so I have sort of, imagine generation number 4. And you would call it, not very imaginative, tau prime, new tau prime, T prime, B prime. Sorry, the language. And you could ask yourself, well, You remember the fourth generation. It is possible that the masses of the, and you establish this, the mass of the tau prime, no, not the capital, the mass of the tau prime. Suppose you find you don't see them, so you say, okay, I know mass of the tau prime, mass of the t prime, mass of the b prime is bigger, even much bigger, say that mw and mz. So for example, w cannot decay into anything anymore. It cannot decay into tau prime plus nu tau prime bar. It cannot decay into t prime bar plus b prime. It simply cannot decay. They're heavier. And so this is very nice. This is what I need. And also the Z boson cannot decay into whatever, into tau prime plus anti-tau prime and so on, cannot decay. But in principle, Z can decay into nu tau prime plus nu tau prime bar. If the force, if they are light, if they are neutrinos. Neutrino means that they're light. The name neutrino means a small, light, little neutron. In Italian, ino is something small. It's a diminutive. This is possible. So what you do the homework. You compute gamma z as a function of the number of neutrinos. After all, you just include another decay. And you can prove that number of neutrinos is 3. This is what the lab proven. Well, experiment doesn't give you number 3. They will tell you that it's, I don't know, 297 plus or minus whatever, but it's an integer. You prove. We knew that there were 3 light neutrinos, so we started to believe that there are 3 generations, maybe if there are only 3 light neutrinos. This was not the proof, of course. It could happen that the so-called tau prime, nu, is very heavy, you never know. But if you follow the generation pattern, you would know that there are only 3 generations. We started to believe in that. Even if you read New York Times, in those days, if you were to read, they will tell you that the experiment proved that there were 3 generations. That was wrong, because this can be heavy, but they've proven that there are 3 light neutrinos, okay. Also, from lab, you can prove that there are no new light particles of any kind. Particles of any kind coupled to Z. Couple has to be ridiculously small. Normally gauge coupling to Z, which is, there are no new such particles from lab. And that you will prove yourself, because you compute the standard model. How do you know that? Well, you compute gamma V theory of the standard model, and you find out that it's equal gamma Z experiment. This is what lab did. This was a great thing of having the factory of Z bosons. When you have 1 billion Z bosons, you see lab is 10 to the 9 Z bosons. Your statistics is very good. It's all about probability. If you and I know the laws of nature are just probability, when the probability for an event is very small, we proclaim a law. For example, I'm sure that you believe in law of gravity, that if I take my cup now and put it in the air, it's going to fall down. That's only probability. Maybe you and I can compute what is the probability that the cup doesn't fall down. I mean, it's an interesting number.
0.
Why 0? How do you know that? How there are no zeros in science. No, that you cannot say. That, please, you cannot say. It's like telling me that the photon mass has to be 0, or the charge of neutrino has to be 0. That you cannot say experimentally. I'm asking you, when I ask you what the probability is, You have to think. No, if I ask you the following question, what is the probability now that all the room in my room goes to a corner and I suffocate myself? It's not zero. We could sit down and compute this number. No, this number I cannot compute about gravity, I agree, because the theory doesn't predict. We built the theory. This is called the universal law of gravity that Newton came up with. Well, Galileo has formulated universally. The stones fall down. Now, why do we believe this? Because you and I we have never seen a stone not falling down. So how many of us there are on the planet? Okay, let's do a little. You want to do this for fun? Let's think a little bit. Let me give you a few important numbers. What time is it? We have a few minutes, okay, as we are chatting, okay? I want to explain something it seems. I find that my colleague scientists and my students don't really know what we mean by laws of nature. You get confused. I used to get confused the way I was taught into proclamations and the facts. And I've noticed I can cheat on you. I can tell you that photon is massless and you don't even question it. No student in my teaching career have ever asked me, why do I say that photon is massless? They said, oh, they were told gauge invariance. You know, okay, this is like first thing, is photon massless? People often say, yes, M is zero. How do you know that? They say from U1 gauge invariance. Now, are you aware that this is stupid? That you are eating your own tail? Because then you will predict that MW is zero also because of gauge invariance. No, experiment says this is not true. No, MW is non-zero. Therefore, there is no gauge invariance. No SU2 gauge invariance. I will break it. I'll break any symmetry if tomorrow they tell me that it's broken. You can't use laws that you establish from experiment to claim that experiment is. I'll give you some nice examples, okay? Please ask me questions here. For example, I wish I was in the Blackboard so to see you guys when I'm teaching this, because this is very fundamental. In the 50s, Reines and Goldhaber, great physicists. Reines got the Nobel Prize, discovery of neutrino. Goldhaber never got a Nobel Prize, but he should have gotten for neutrino helicity. He was my colleague at Brookhaven National Lab. So we used to talk a lot about this, about the problem of education over coffee. I'll try to find some published notes of Goldhaber. He once gave a nice interview speaking about the confusion about the problem of physics teaching, what people confused. So they wanted to measure proton lifetime. They are going to the funding agency and asking money to measure proton lifetime. How big is it? So this is them, great physicists. Now, the funding agencies says, you guys are crazy. Proton lifetime is infinite. They say, so Reines and Goldhaber and Reines. Why you say that? Funding agency, let's call them FA. Funding agency says, because baryon number is a good symmetry. Delta B is zero. Proton carries a baryon number. Goldhaber and Reines, why do you say that? Funding agency. There is a fantastic limit on proton lifetime. It's so big, 10 to the 18 years. By the way, it comes from Goldhaber. He puts the first limit. It's beautiful. From, you know, he calculates the probability if proton decays, then you and I are going to die from cancer much before we decay. the radiation will kill us. So he gets the numbers, and from the fact that you and I live an average, I don't know, 80 years, he puts the limit on. This is worth doing sometimes, you know. We could discuss this in the office hours, but I just want to emphasize the point now, and I'll be very brief. So they say it's so big that there must be a baryon symmetry, they say. And then Gene Reiner say, but we want to measure that. And that we went to Ons and Ons. They took months to get the money because these guys got confused. And you may get confused. Although I gave you this example and you can see this is really stupid. Why? Because people proclaim a certain thing and then forget why they proclaimed it. This is exactly like the photon mass. The reason we believe photon is massless, not because of gauge invariance, but because the number is very small, we started to believe. By the way, today, nobody believes that proton is, nobody believes. I cannot find anybody. Well, nobody is, people I know, believes P is stable. And because of the experiments, they got the money from funding agency. And today, the proton limit lifetime, someone has an idea how big is the proton limit lifetime to get the numbers? This is Kamiakande experiment in Japan. Any idea? 10 to the 34 years, maybe even 10 to the 35. The limit has been approved because those guys got the money. They pioneered this research, okay? But now the limit is so big, yet nobody believes it's stable. We are all sure that the baryon number is non-zero. People are sure. Why? Because the theory gets involved. It's called grand unification that predicts this. And there is no reason that the number which is large should be infinite or number that is small should be zero. It's very interesting. Anyway, one last example is the falling of stones. Let's see why we believe in falling of stones. How many people there are on Earth? About 10 billion, shall I approximately say? There must be about 8 billion. Am I right? Who can help me? About 10 to the 10 today. So how many people have populated Earth up to now? If I take history, I think this number, if I take about, is it 10 billion, right? If I take 10 to the 12, because their population is very small, is the population throughout history. And how many times you have seen, each person has seen, how many times in your life you see stones falling down? What would you say? Objects falling down? 1,000 times? Someone wants to help me?
It's more than 1,000. 10,000.
10,000? What number do you want? 1 million? Is this good?
Sure.
I'll tell you the following. Look, I'll be nice to you. Let me imagine that each person, that's impossible, by the way, sees 10 to the 9, which is 1 billion, stones falling down. You don't see that many, you agree? You don't live that long. Do you agree? Less than 10 to the 9. So in other words, we have less than 10 to the 21 stones that have been observed falling down objects. So I tell you what the probability that my cup stays in the air is not zero. That I cannot say. All I can say is that it's less than 10 to the minus 21 by this number. It's probably bigger than that. In the end, notice that this number is not so small. Look how big this number is. Proton lifetime is 10 to the 34 years. What is the muon lifetime? Roughly. I need you to know have the sense of
10 to the minus 20 something.
10 to the minus?
23 or something.
In what?
Seconds.
No. No, you cannot decay that fast. That would be a strong interaction. It's about 10 to the minus 6. So in other words, look at this interesting thing, that tau proton over tau muon is bigger than, what is this number? Oh my God, I think a year has about 10 to the 8 seconds. Actually, I think it has people, there is always a pi. I think the number is pi times 10 to the 7, roughly. In physics, roughly 3, doesn't matter. So I'll take 10 to the 8. So this is 10 to the 42 seconds. So it's a number which is bigger than 10 to the 48. Yet we don't believe it's infinite. In other words, you should say, oh, when the number is so big, then the probability, is 10 to the minus 48. But because there is a theory that predicts it, now most of us believe that proton will decay. And because there is no theory that predicts the breakdown of Newtonian, Einstein agrees with Newton that the stones are falling down. So everything is probability, okay? Please remember that. Physics that I want you to do, please, among other things that takes you into doing speculation, is sometimes not even understanding what science is. Science is just laws of nature are statistical. Then we formulate the universal laws. And most of the time, these universal laws last and then turns out to be incomplete. And we find deviations. So many of our prejudices have gone away because the experiment showed us that. So I have a few more minutes and I want to ask the question for you so that I can go on with this course. I hope you're appreciating what I'm telling you now. For example, let me ask you the following question. Let me get the feeling. It surprised myself. I didn't have a good feeling with the number. I had to remind myself. You and I say, for example, you would agree that you and I are classical objects. You agree? Or my car is a classical object. You agree? Newton is good there. I'm surely not quantum mechanical. But for example, proton is not classical. Let me remind you why proton is not classical. Why do I say the proton is not classical, by the way, by quantum mechanical? Why do I apply quantum mechanics to a proton, but not to myself?
Is it because of the de Broglie wavelength?
In a sense, right, we can say it nicely, quantum mechanical objects satisfy this I H bar. H bar is 1. So in other words, if I take a static proton, and I take the mass of the proton times the size of the proton, they should be roughly of order 1 for a quantum mechanical object in the units of H bar. And it is, by the way, the mass of the proton is GeV, and this radius is about 10 to the minus 14 centimeters, which is GeV to the minus 1. Proton is quantum mechanical. So let me ask you, since it's all about probability, can you tell me to what precision I am? So let's see, Goran. I know I'm classical, but to what precision? In other words, how small are quantum mechanical effects in my case? Are they 10 to the minus 3, 10 to the minus 5, 10 to the minus 10? You have any idea? Think about this. You are students of physics. You're going to be researchers, and you go to the party, or you are buying a lunch at the cashier, and the cashier person asks you, but you know, there is this quantum mechanics. Can you tell me why don't I have to know about it? What is the probability that I must include it? You should have some idea. Just try some number, please. I want to see your feeling for number. I was wrong, by the way. Don't feel bad because I was wrong. I forgot the number recently. I reminded myself very recently, some years ago. I don't teach quantum mechanics. Otherwise, if I teach quantum mechanics, you know, I didn't teach quantum mechanics. We didn't have. Just I need some, you know, before we split. Look, we are going to split in a few minutes.
Can't we calculate it like roughly?
Yeah. No, we will calculate it. I want your feeling for this.
Yeah, then like take the mass
No,
of the average
I'm
proton.
asking you for the result. What do you think is the precision of this? Just make a guess.
Around the order of h bar.
10 to the minus? No, there is a number, not h over the bar. H bar is 1. There will be a probability that I'm quantum mechanical. The will be 10 to the minus something. The quantum mechanical correction, if you wish. Quantum mechanical correction to me is of order 10 to the minus something. This is what physics is. Everything that we say when I ignore, when I tell you, when I ignore the electron mass in the W decay, what is the precision that I ignore it? It was 10 to the minus 5, remember, in the W decay. So what do you think is a quantum correction to Goran? Or any of you will make an estimate. 10 to minus what? I need a guess.
34.
Oh, you are good. You know the number is small. I'm glad to hear that because people sometimes tell me it's 10 to the minus 10. Let's do it. So what is my mass? Well, let's take the mass of the Goran. Let's take 100 kilograms. Order of magnitude, do you agree? It's I actually weigh less, 78 or something, but let's say that's 100 for physicists. What is my radius? What is the, how did I call it? R Goran is about a meter, you agree? Order of magnitude. So in other words, from here, M Goran times R Goran. Do you know that kilogram is 10 to the 27 GeV? There are 27 protons in a kilogram. You remember this? So this is 10 to the 29, 100 kilograms, and 1 meter is 100 centimeters. So I have GeV times centimeter. So this is 10 to the 31, GeV times centimeter. But if you look back, GeV times centimeter is 10 to the 14. So this is 10 to the 45. For proton, it's 1. And I got 10 to the 45. In other words, the quantum mechanical correction for Goran, or for you and me, I took myself, is 10 to the minus 45. I'm 10 to the 45 orders more classical than proton. It's sort of, it's nice when we do the things, you know, because you see what may happen, that it may happen that some of you want to work on quantum gravity. I had a feeling that a number of you want to work on quantum gravity. Am I right? Are there people of you that are interested in quantum gravity? After all, you want to do ATS-CFT or strings. That's all about quantum gravity. Or do you know? So if you want to do these things, do you know that that's because of quantum gravity? There is nothing else this theories bring. They don't change the standard model, surely. So there must be, but you don't answer yes. It's very interesting. You want to do strings or ATS-CFT? I have to talk to you guys why you want to do that if it's not because of quantum gravity. Do you want to tell me, some of you, why you want to do this? One answer I don't accept because other people do it. Physics is natural philosophy, says Newton. And all the great repeats it. Weinberg used to use it a lot. And let's even say Goran. I've been insisting this more than anybody I know. If you look at our archive, I have recently a very provocative paper for those of you, but you will not understand it. Natural philosophy versus philosophy of naturalness. I'm criticizing the, by the way, nobody objected to it. None of the people that were so opposed to, I'm known well enough that people should object to it. I am yet to find someone disagreeing. So that means natural philosophy, it's describing phenomena of nature, okay? So, well, anyway, even if you're not interested, the reason people introduce strings or ADF-CFT is because of quantum gravity. They claim that they have to modify Einstein theory. Nothing else is needed. This is from strings. That's why the world went crazy, or ADS-CFT, or all these things. Okay, formally. Do you have any idea how small the quantum gravitational effects are? Did your teacher ever help you with this? For example, in general relativity course, that's one of the things that I will show to people, that the number is so small that there is absolutely no sense in thinking about it unless you want to really work on some very interesting formal mathematical question and you don't care about physics. I don't want to put the number today. This is a fair moment to stop the lecture. I hope you appreciate this digression. I felt I had to do it because I'm sometimes worried. I've seen this, you know, I'm teaching a very advanced course. I just gave a course on grand unification in LMU and Munich. And I saw a similar thing, that it's a universal pattern, that the development of strings and other similar directions have somehow killed the physics the way was taken seriously by people by Weinberg, Lesher, and who try to understand the laws of nature, so that the students ought to know, to have a sense of the sizes of numbers. Okay, I hope it was not totally useless. Just a reminder. Okay, I can stop. I think I'm really on time now today. Maybe 2-3 minutes more. I would appreciate any comment or question regarding this.